I think that we can introduce our wonderful speaker today, Kai Yang. Thank you, Kai, for accepting the invitation. It is really wonderful to have you here. So let me just give you a background of Kai. So Kai got his PhD in 2015 from the Institute of Physics and Beijing National Lab. Then afterwards, he moved to IBM Almaden, where he was working as a postdoc. And in 2021, he started as associate professor in the Institute of Physics and Beijing National Lab, where he's leading his own research group. So Kai has been working on scanner-electronic microscopy, and in particular on designing nanoscale quantum magnets. And in particular, he has been spearheading some of the perhaps most impressive results on ESR in individual atoms with STM, and in particular showing how one can use ESR to probe quantum excitations in quantum magnets, and in particular to try to create new quantum magnets by atomic manipulation, atom by atom. And today he's going to tell us about atomic scale magnetic resonance of spins on a surface. And I think that with this, I can let our wonderful speaker start. So Kai, thank you so much for accepting the invitation today. It is a great pleasure to have you. We look forward to your talk, and the floor is yours.
Okay, so Jose, thanks for the nice introduction. So it's really my great pleasure to present our work in this wonderful colloquium series. So I have been watching this series and I have learned a lot from it. So today I would like to give you an overview about the spin resonance STM, or the ESR STM, and what we can do with this new technique. So this is mainly about the detection and control of the surface spin states. So most of the data that I will show you today was measured at IBM Research Lab in Almaden, and when I was still doing a postdoc there. And recently I have moved to Institute of Physics, Chinese Academy of Sciences, and currently I'm starting to build my own lab. Okay, to start with, first let me remind you the basic principles of the spin resonance. So let's consider a spin one-half particle such as an electron. So when we apply an external field, the spin up and spin down state are separated by the Zeeman energy. And to drive the spin resonance, we need to apply an AC magnetic field. And we also require the direction of the AC field is perpendicular to the DC field. So when the frequency of this AC field equals the Lamarck precession frequency of the spin, this AC field can drive the coherent transitions between this two-level system. And correspondingly, this AC field can easily rotate the spin between the spin up state and spin down state, and back and forth. So you can see here the spin dynamics can be decomposed into two motions. So the first is the Lamarck precessions around the z-axis. This is due to the DC field, and also we have the change of the angle between the spin direction and the z-axis. This is so-called the Rabi oscillations. Okay, so what we learned from here is that we can use an AC magnetic field to easily control the spin state as long as we are in resonance. Okay, so the most important applications of the spin resonance is the magnetic resonance imaging in hospitals, where the doctors can take an image of the patient by measure the nuclear magnetic resonance signals of the water molecule. And it is also very useful too for exploring the basic science. For example, people have used the spin resonance to study the local spin distributions of molecular magnets. And also people have used the spin resonance to probe the magnetic properties of some exotic quantum materials, such as several quantum spin liquid candidate materials. But the downside of this conventional bulk spin resonance is that the detection of the signals requires a large number of spins. So this is because here the spin resonance signals is basically the macroscopic induced current in this so-called receiver coil. So this requires a lot of spins. For example, for the electron spin resonance, it takes about 10 to the 7 electron spins to have enough signal noise ratios. So this means the bulk spin resonance doesn't have enough spatial resolution, and it cannot be directly used to study the quantum behavior of the individual spins. So this is the why over the last 2 decades, there's a lot of effort into realizing single spin magnetic resonance. So this is the also very important in the context of quantum computing, because it can allow us to have a single spin qubit. So, single spin qubit has been realized in many different platforms, such as the quantum dots and semiconductor impurities, such as the phosphorus donors in silicon, and also this the nitrogen vacancy sinker in diamond. And it is also shown that the nuclear spin state of the magnetic molecule that is bridged into metal electrode can also be used to process the quantum information. So using these platforms, people have demonstrated a simple quantum computing algorithm, and also have used them as a sensor, especially the n-wave center, to probe other quantum materials. For example, people have used n-wave to probe the single protein molecules, as well as some interesting magnetic 2D materials. And recently, there's also some interesting demonstration of the quantum simulations of Hubbard model using the quantum dots. So this is the very promising field. And so today I would like to introduce our single spin qubit platform based on ESR STM. So this is the magnetic atoms on the surface. The surface can be, for example, the magnesium oxide. And so this oxide layer can decouple the surface spin from the underlying metal electrode, so that we can have a longer spin lifetime. And we can also put many different types of atoms on surface, such as these transition metal atoms, titanium, iron, copper. And so different atom has different spin properties. So one of the unique advantage of our platform is that we can use STM manipulations to build this artificial quantum magnets, and we can then probe their quantum states with atomic resolution. So this is very difficult to realize in other platforms. So in order to detect and control the quantum states of the surface atoms, we combine our STM with the electron spin resonance. So these combinations give us a spatial resolution of sub-angstrom and also a simultaneous energy resolution of tens of nano eV. So this makes the ESR STM a very powerful tool to probe the surface spins. And in the future, we also expect the ESR STM to be useful to probe other quantum materials. So, here is a history about the development of the ESR STM at IBM Melbourne. So the single atom ESR was first measured iron atom MgO in 2015. And later we show that it also works on other magnetic atoms, such as titanium and copper. So using the ESR STM, we can also look at the spin-spin interactions of surface atoms, such as the magnetic dipolar interactions, the Heisenberg exchange interaction, and even the hyperfine interaction between the nuclear spin and the electronic spin. And 2 years ago, in 2009, we finally showed that we can make this surface atom into the quantum bits by showing this quantum oscillatory behavior. So this is realized by the so-called pulsed ESR measurement. Okay, so here is an outline of today's talk. So I will basically introduce 3 simple applications of the ESR STM, including the magnetic sensing, the simulations of the quantum mechanism, as well as the pulse ESR. So this is about the coherent control of the spin state of the surface atom. Okay, so the first question that you may ask is, how do we drive the ESR in STM? So as we discussed earlier, so to drive the ESR, we need an AC magnetic field. So in our STM setup, we take advantage that we can have a huge AC electric field in the STM junction. So when we apply this huge AC electric field on the charged surface atom, it can induce the oscillations of the atom in the vertical direction or other direction. So since we also have the magnetic interaction between the surface spin and this magnetic tip, so this piezoelectric motion of the surface atom can induce an effective AC magnetic field, and the strength of this field can be as large as 20 millitesla. And then we can then use this AC field to drive the spin resonance of the surface atom. There are 3 advantages of this electrically driven ESR technique. First, it is very local. So because here the AC field is only applied on the atom under the STM tip. And second, it produced less heat compared to just running, for example, 100 nanoamp current transmission line cable nearby. And thirdly, so the strength of this AC field is very easy to control because we can just by changing the tip atom distance. So this the exchange interaction-driven ESR-STM mechanism was first proposed by Jose and his collaborators in 2017. And later we confirmed this proposal in the later experiment. So of course, there are other possible ESR-STM mechanism. And so if you are interested, you can read this Science Advanced paper published last year. So this is a very good paper. And there's a summary of several possible ESR mechanisms. So here in our ES-STM setup, we applied the RF voltage directly on the STM tip. And it is also possible to induce an AC electric field across the STM junction using an antenna nearby. So this idea was first designed and realized by Professor Gamardella's group in 2020. And people also use this setup to study, for example, the photon-assisted tunneling of a superconducting tunnel junction. So before we can measure the ESR signal in STM, it is very critical to characterize the transfer function between the microwave source and the STM junction. So this is because during our measurement, we keep the external field constant, and then we sweep the frequency of the microwave generator. So that means we can observe the cabling resonances due to the reflections of the RF signal in the cable. So the cabling resonances can be easily misinterpreted as spin resonance signals. So we need to get rid of this cabling resonances. So to get the transfer function, of course, we need to know the RF voltage that is applied across the STM junction. So the key use of the nonlinearities of the IV curve to convert this high frequency RF voltage into an averaged DC current. And then we can easily measure this DC current and learn about the amplitude of this RF voltage. And then we can obtain this transfer function at different frequencies. And as you can see, there's many peaks and dips. And to get rid of them, we ask our microwave generator to produce a frequency-dependent RF power. And so this is basically an inversion of the transfer function we just measured. And by doing this, we can eventually have a very flat background over a large range of frequencies. So here the y-axis is the VRF, which is the RF voltage that is across the STM junction. So this the transfer function flattening process is what we did every day in the lab, because it turned out this transfer function is also very sensitive to the liquid helium levels. Okay, so once we get this flat background, we can measure the ESR spectrum of a single atom, such as a spin 1/2 titanium atom. So here is the frequency, and the y-axis is the ESR signal. Which is basically the tunneling current measured by the locking amplifier. And so this is the ESR peak, and the line width of the peak is a typical value is 10 megahertz. So this corresponds to an energy scale of 14 nano eV. And this also basically determines the energy resolutions of our ESR-STM. And this energy resolution is about 1,000 times better than the conventional DIDV spectroscopy that is commonly used in STM. But the DIDV is somewhat limited. And so here from the line width of the peak, we can also estimate the quantum coherence time T2 of the titanium spin, which is about 100 nanoseconds. We can also learn about the energy relaxation time T1 by a separate pump-proof measurement. And so the T1 time is about 190 nanoseconds. So here the ESR signal was read out by monitor the change of the magnitude resistance of the STM junction. So this is because depending whether the spin is on resonance or off resonance, we have different spin populations of the spin 1/2 two-level system. That means we will have different magnitude resistance of the STM junction. Okay, so as the first application, let me discuss the magnetic sensing at the single atom scale. So the idea is very simple. We just put a sensor atom near our target atom. And then by looking at the magnetic dipolar interactions between these two atoms, we can learn about the magnetic properties of the target, such as the direction and amplitude of the magnetic moment. So here the target is near a sensor, and we don't run current through the target directly. So for example, we can use iron MgO as the sensor and to look at the magnetic properties of the nearby holmium atom, which is the 4F transition metal. So when we measure the ESR spectrum of the iron, we found the ESR peak can appear at 2 different frequencies. So this 2 frequency actually corresponds to the 2 different magnetic orientations of the holmium. So for example, when the magnetic moment of the holmium is antiparallel to the external field, it can produce a magnetic dipolar field that is parallel to the DC field. So this makes the iron experiencing a larger Zeeman field. So correspondingly, the ESR peak will shift to higher frequencies. So when the holmium atom flips its magnetic moment, the ESR peak will shift to lower frequencies. So this means by monitor the ESR peak position of the iron, we can monitor the magnetic switching of the holmium with respect to time. So we found at the very low temperature, the holmium can maintain its magnetic orientations for a couple of hours. So that means we can use the holmium, the magnetic orientation of the holmium to store 1 bit of information. So we can easily extend the system from 1 bit to 2 bits using 2 holmium atom. And we can then use a voltage pulse applied on holmium atom to switch these 4 possible magnetic states of this 2-bit system. We can then use an iron sensor nearby to distinguish these 4 different states. So here, because the atomic the distance between these 2 atoms is very small, it's only 1 nanometer. So the corresponding data storage density is very high. It's about 1,000 times better than our current hard disk drive. Okay, so we can not only probe the electronic spin, we can also detect the single nuclear spin of surface atom by probing the hyperfine interactions between the nuclear spin and the electronic spin. So for example, here we studied single copper atoms on MgO. So the copper has 2 different isotopes, copper 63 and copper 65, and both of them had a nuclear spin number 3½ And it turned out the copper electronic spin is the spin 1½ system, and we can confirm this by measure the DITV spectroscopy as a function of different magnetic field. So here is the energy level diagram of this coupled electronic nuclear system. And so let's understand it step by step. So first, let's consider the Zeeman energy of the electronic spin, so which separates the energy levels into 2 different branches. Here is the spin up, here is the spin down of the electronic spin. And then we can consider the hyperfine interaction, which further split each branch into 4 different levels. And we can label this 4 different levels by the nuclear spin number, Mi. And as you can see from this energy level diagram, we have 4 possible ESR transitions, and correspondingly, we have a 4 ESR peak. And also this 4 ESR peak corresponds to the 4 different magnetic orientations of the nuclear spin. So from splitting of the ESR peak, we can also obtain the hyperfine constant. And we found that there are 2 possible values of the hyperfine constant value. And from this, we can distinguish different copper isotopes with single atom resolution. And we can not only look at the copper nuclear spin, we can also polarize the nuclear spin by the spin polarized current. For example, here, let's assume that the tip magnetic moment is parallel to the copper electronic spin. And then when we apply a negative bias, which corresponding to a spin polarized current flowing from the sample to the tip, we can polarize the copper nuclear spin into -3½ states. So here is the corresponding ESR spectrum And here the ESR peak height, roughly speaking, is proportional to the populations of two different nuclear spin states. And so when we flip the spin polarized current using a positive bias, we can polarize the copper nuclear spin into positive 3.5 states. And we also found that we can use the amplitude of the current to control the degree of nuclear polarization. And eventually, we can achieve 30% of nuclear polarization at large spin polarized current. And this corresponds to an effective nuclear spin temperature of 200 millikelvin. And this is about 6 times cooler than our experimental temperature of 1.2 Kelvin. And so to understand this, the current induced nuclear spin polarization, and we proposed a model which basically consists of 2 steps. So in the first step, the spin polarized current first polarize the copper electronic spin by a spin flip transitions in a STM junction. And so this process corresponds to the pumping of the populations from this 4 lower levels into the 4 upper levels, as indicated by the 4 blue arrows. In the second step, the copper electronic spin exchange its angular momentum with the copper nucleus, and through this spin flip-flop part of the hyperfine interaction. So this corresponds to these 3 pair of transitions, as indicated by the dashed arrows. So eventually, the spin populations will flow according to this zigzag patterns, and eventually we can polarize the nuclear spin into positive 3.5 states. Okay, so since we can polarize the nuclear spin, that means we can initialize the nuclear spin. So we can then demonstrate the measurement of the nuclear magnetic resonance of a single copper atom. So this is done by applying an RF voltage with a frequency that matches the nuclear spin levels around 1.5 gigahertz. So here is the NMR spectra of 2 different copper isotopes. And we can see they have slightly different NMR frequencies. This is because they have different hyperfine constant. So in our experiment, we also found that as we vary the tip magnetic field that is applied on the copper atom by just changing the tip height, the NMR frequency also shift accordingly. So this means maybe in the future, we can use the NMR spectrum of the single atom to probe the magnetic environment of the electronic spin. So this work is basically the first demonstration of single atom NMR using the scanning tunneling microscope. Okay, so using the ESR STM, we can also study the quantum mechanism. So the idea is to use the magnetic atoms as building blocks to build these artificial quantum magnets with the tunable geometries and magnetic interactions, so that we can realize the different Heisenberg model, and we can then probe their quantum eigenstate by measure the ESR spectrum. So the simplest system is, of course, the 2 interacting spins. So here is a corresponding spin Hamiltonian. And so the first 2 terms is the magnetic interaction, and second 2 terms about the Zeeman energy. And we can use the STM manipulation to control the properties of the magnetic interaction. And we can also use the external field as well as the tip magnetic field to control the different Zeeman energies of the different spins. So let's still use the titanium atoms on the MgO as example. And so what we can do is to use atomic manipulations to precisely control the relative positions of this 2 titanium MgO, so that we can realize an anti-ferromagnetic dipolar interactions or ferromagnetic dipolar interactions. So depending on how we arrange these 2 magnetic atoms with respect to the external field. So when we bring this to atom a little bit closer, we can also make the exchange interactions dominant. So correspondingly, we saw a rapid increasement of the ESR peak splitting, so which is proportional to the coupling strength of these 2 magnetic atoms. So, so in our experiment, we also built many atomic dimers with different relative positions and relative orientations. And we can then use this spin Hamiltonian to fit the ESR splitting. And from that, we can obtain important parameters of the spin Hamiltonian. such as the magnetic moment of the titanium, which is 1 MeV, because the titanium atom is a spin-half system. We can also obtain the decay constant of the exchange interaction, which is around 0.4 angstrom. So that means at 3 lattice constant away, we have a coupling strength of about 1 gigahertz. So this is about 4 micro eV. So in addition to study the interactions between the surface spin, we can also probe the interaction between a surface spin and the magnetic tip. So this effective interaction, this magnetic interaction can produce an effective the tip magnetic field applied on the titanium atom and the tip. And so we can characterize this the tip magnetic field by measure the ESR frequency shift as the function of the tip height. And from that, we can obtain that the amplitude of this tip magnetic field can vary between 1 millitesla and 10 Tesla. So this is over 4 order of magnitude. We can also know that the angle of the tip moment can vary between 10 to 70 degrees with respect to the external field. So here, the highly tunable the tip magnetic field give us the additional control knob to control the coupled states of the surface spins. For example, we can use the tip magnetic field to control the degree of state mixing of the two coupled titanium atom. So as we increase the tip magnetic field, we found that the quantum eigenstate is detuned from this singlet triplet state into the semi-product state, which is the 0, 1, 1, 0, 0, 0, and 1, 1. And we can also, so here, the reason the energy level is detuned by the tip field is because here the tip field is only applied on one of the surface atoms. So this breaks the magnetic symmetries of the two titanium spin. So we can obtain the change of the energy level diagram by measure the evolution of the ESR spectrum as a function of the tip magnetic field. And for example, here we can see there's some nonlinear frequency shift of the ESR peak. So this actually corresponding to the nonlinear energy level shift of this coupled two-level system because of the avoided level crossing. So what we learned from this measurement is that even here the STM tip is only interacting with only one of the spin, we can still probe the coupled spin states. So this conclusion is very important for us to study larger coupled spin structures. So as the number of coupled spin increases, so the spin will have more than one way to do a spin pairing with each other. For example, here let's consider force spin with nearest neighbor coupling. So for this force spin system, there are two possible spin singlet configurations. And so here each ellipse corresponds to a spin singlet state, which is the superposition up, down, down, up. And so the ground state of the system is actually superpositions of the singlet configurations. And so this is very similar to the resonating bond of the benzene molecules. So this is why this is called the resonating valence bond state. So the reason we are interested in this RVB state, because this is close related to the quantum spin liquid. And so quantum spin liquid is very exotic quantum state with, for example, the fractionalized excitations as well as long-range entanglement. So on the MgO surface, we can realize this RVB state using the titanium atoms. So basically, we use the STM tip to apply voltage pulses on top of titanium atoms so that we can control their adsorption site. And eventually, we can build this 2x2 spin structures. And you can see here, there are two different heights of the titanium atoms. So this corresponding to the two different adsorption sites of the titanium MgO. So in order to probe the quantum eigenstate of these 2x2 spin structures, we measure its.
Hi, okay, sorry for interrupting. There's one question in the chat. And the question is, why did you use inelastic spectroscopy instead of ESR when the effective tip magnetic field is large? Is ESR not suitable for a large magnetic field?
Yes, because the largest frequency we can apply is about 40 gigahertz. So 20 gigahertz is about 0.1 millieV. So that means above about 0.2 milli eV. So it is out of the bandwidth of our ESR-STM measurement. Then we can actually switch to the DIDV measurement, which can allow us to further measure the large ZIM energy because of the larger tip magnetic field.
Yeah, right, great, thanks a lot.
Okay, I will continue. So to measure the quantum eigenstate of the 2x2 spin structures, we measured the ESR spectrum, and from that we can learn about the energy level diagram of this coupled spin system. And it should be pointed out here that for these 2x2 spin structures, the ground state is actually ferromagnetic states because the coupling is smaller than the external field. So, but we can still have access to this RVB state by driving the coherent transitions, for example, from the ground, from the first excited state into this RVB state. So this transition corresponds to this ESR peak right here in the middle of these three spin structures. And to learn more about this quantum eigenstate, we also study the evolution of the ESR spectra as a function of the tip field. And from that, we can extrapolate the energy difference between the RVB state and this ferromagnetic arrangement. So this basically characterized the energy gain by forming this spin singlet superposition. And so the value we obtained is very close to the value from the direct diagonalization of the spin Hamiltonian. And in comparison, for the classical neo state, the energy expectation value is much higher. So that means we indeed have this RVB state as a quantum eigenstate for the 2x2 spin structures. And we can use the STM tip to build another 4-spin structure with different boundary conditions. So here we have a 4-spin chain. And because we have an even number of spins, so the ground state is still a spin singlet. It's superpositions of different spin singlet configurations. But now we have a different weight because for this 4-spin chain, the interaction between the first spin and the S1 and S4 is much smaller than the nearest coupling. And to get more information about this 4-spin chain, we measure the ESR spectrum at different atomic site. And as you can see here, for Sims transition, for example, transition 1 from state 1 to 2, they involve differently depending where we parked the STM tip. And from that, we can actually qualitatively understand the spin polarizations of the state 2 that is distributed between these 4 atomic spins. Okay, so up to now, everything is about continuous wave ESR. So that means during our measurement, we turn on the RF voltage all the time, and we are detecting that is the steady state of the system. And so if you want to learn about the coherent evolutions of the spin state and understand their to learn about the quantum phase, we have to use the pulse ESR. So which requires a precise control of the width of the RF pulse. And so this is because depending on the time durations of the microwave, we can rotate the spin from the initial state to different angles in the Bloch sphere. And so to implement the pulse ESR, we used an arbitrary waveform generator to electronically get the microwave generator so that we can control the width of the microwave. And then we detect the change of the tunneling current through a locking amplifier. So using this setup, we can measure the rapid oscillations of a single titanium spin. So here's the data. And the x-axis is the pulse width and the y-axis is the locking current. And so the oscillatory behavior corresponds to the spin rotations between the spin up and spin down state and back and forth. And so different curves were measured at different RF power. And at the largest power we can apply, it takes about 25 nanoseconds for the spin to go from 0 to the 1 state, so-called pi rotation. And you can also see that this oscillation decays away up to 4 to 5 oscillations. And so from the decay constant, we can learn about the quantum coherence time T2, which is about 14 nanoseconds. And so here, this Rabi oscillations was measured at the resonant conditions. And as a sanity check, we also measured the Rabi oscillation at a detuned frequency. So that means the microwave frequency is slightly different than the resonant frequencies. So for this condition, the spin will experience an additional field along the z-axis in the rotating frame. So as a result, the spin will have a larger Rabi frequency, but the amplitude, the oscillation amplitude will be reduced because now the spin will oscillate around this axis and it cannot reach the source pool anymore. And so here is experimental data. And so although the signal noise ratio is not very good, but you can still see that as we detune more from the resonant conditions, the Rabi frequencies increases correspondingly. And on the right-hand side is the simulations, and they agree very well. And we have two ways to control the amplitude of the Rabi frequencies, which basically characterize how fast we can control the spin states. So the first is by using the RF voltage. And we can see as we increase the RF voltage, the Rabi frequency increases monotonically. So the second way is by changing the tip atom distance. And we found that the Rabi frequencies increases exponentially as we decrease the tip atom distance. So this is very easy to understand because here we drive the ESR through the exchange interactions between the magnetic tip and the surface atom. And we know that the exchange interactions also has an exponential dependence with the distance between these two atoms. So during this measurement, so as we decrease the tip height by increasing the DC tunneling current, we notice that the T2 time also decreases. So this actually indicates that one of the major decoherence for the titanium spin is the DC current. So let's look at the decoherence sources of the titanium spin. So in addition to the DC tunneling current, so the titanium spin on the surface is also influenced by the scattering electrons from the tip back to the tip, and also from the underlying silver back to silver. So these two channels contribute to an effective current of 10⁻². So in addition to this scattering electrons, the quantum coherence time T2 is also influenced by the slow noises during the measurement, because the Rabi oscillation data I have just shown was the average result of many repeated experiments. So that means any slow variations of the, for example, the resonant frequencies F0 and also slow variations of the Rabi frequency omega can make the envelope of this Rabi oscillation decay faster. So in order to increase the quantum coherence time so that we can perform more quantum operations, and we use the multiple pulse sequences. So the first pulse sequences we tried is the Ramsey, so-called Ramsey fringes. So it consists of two half-pi pulses along the x direction, and in between it's a free evolution time for the spin. So during this measurement, we detuned the microwave frequencies on purpose. So that means during this free evolution time, the spin up and spin down state will pick up a relative phase. So for example, if you wait for the right amount of time, the spin will be brought back to the original state. So here, the first half-pi pulse brings the spin from the initial state to the -y direction. And so this is the spin rotations during the free evolution time. And the final half-pi pulse brings the spin back to the original state. So, so as we vary the free evolution time, again, we can observe this quantum oscillatory behaviors of the tunneling current. And so the decay constant give us another estimate of the T2 time. And but unfortunately, the value we obtained is very similar to the value we obtained from the Rabi measurement. So this actually tells us the current induced by the RF voltage and also the slow variations of the Rabi frequency. They are not the dominant decoherence sources for the titanium spin on MGO. So in following, we then tried the spin echo pulse sequences and compared to the Ramsey. So it consists additional pi pulses in between the two half-pi pulses. So the purpose of this spin echo pulse sequence is to remove the slow noises between different measurements. So to understand how this spin echo works, so let's consider two different measurements. And so let's assume in the first experiment, the spin experiences a noise that points to the North Pole, as indicated by this red dashed arrow. And in the second experiment, the spin feels noise pointing to the South Pole, as indicated by this blue dashed arrow. And then, so now let's turn on the spin echo pulse sequence. And we can see, although the two spin evolves differently during the spin echo, they are both brought back to the same state after the spin echo is finished. So this means we can kind of cancel the differences in noises between the different measurements. So using this spin echo pulse sequence, we can eventually increase the T2 time to 190 nanoseconds. So this is about 5 times better than before. So this means the major decoherence for the titanium spin is actually the slow changing tape field, and we can use this spin echo pulse sequence to dynamically decouple the titanium spin from this effect. So in addition to study the spin single qubit, we can easily extend our system to 2 qubits using STM manipulations, so that we can have a larger Hilbert space to explore. So in our experiment, we first built this so-called Weaklycoupled dimer. So that means the magnetic coupling between these two atoms is much smaller than the Z energy difference between two spins due to the presence of the tip magnetic field. So here is a corresponding energy level diagram. So the eigenstate is the Zeeman product state 0, 0, 0, 1, 1, 0, 1, 1. So we first characterize this energy level diagram by measure the ESR spectrum, and we found there are 2 ESR peak which occur at 2 different frequencies. So this is very good for us, because that means we can choose to drive on one of the transitions, such as this blue transition. So this blue transition corresponds to a transition between 0, 1 or 1, 1 state. Or we can say that this corresponds to a conditional flip of the first spin, which is a spin and the tip, only when the second spin in the 1 state. Similarly, we can also choose to drive this red transitions, which corresponds to a conditional flip of the first spin, only when the second spin in 0 state. So this is basically a very simple demonstration of the quantum synod gate between the 2 qubits. So the key to realize this selectively driven synod gate is to have an unevenly spaced energy level diagrams. So the similar idea have also been previously used in the molecular magnet system to realize the quantum synod gate. And of course, you can also use the multiple pulse schemes to realize the synod gate if you can individually control 2 qubits and also have a way to turn it on off their magnetic interactions. But this multiple pulse scheme has much better scalability as the system grows larger. So we can also bring this to atom closer, and then we have this strongly coupled dimer. So this means the magnetic interactions is dominant over the tip magnetic field. So correspondingly, we have this superposition state of 0, 1 and 1, 0 in the quantum eigenstate. And so we first characterize this energy level diagram by measuring the single atom ESR spectrum, and we found there are 4 ESR peak. So we have 4 peak instead of 2 peaks, because here the state mixing makes more transitions available. So similarly, we can choose to selectively drive one of the transitions, such as this blue transition, which corresponds to the coherent rotation of the system from the ground state 0, 0 to this blue mixed states. And we can also choose to drive the red transitions, which correspond to the rotation to the ground state, from the ground state to the other superposition state. So this results shows that we can use the pulse ESR to prepare some interesting quantum state. Maybe in the future, we can study their time evolution using the Pompero measurement. So this is all the data I want to show you today. And finally, let me thank all my team members at IBM, especially Chris and Andreas for their help and support during my stay at IBM. And also our wonderful theory collaborators, Joaquin, Alejandro, Jose, and Jiang for their great theoretical support. And so here I list 3 possible future directions we can further pursue with the ESRTM. So the first is about how to drive more qubits. So the idea is to make use of the AC electric field in the STM junction instead of the exchange field. So here the electric field is more extended than the STM TIF field. And then we can put an additional magnetic atom nearby. And then we can use the field gradient produced by these magnetic atoms to drive the atomic qubit that is not directly under the tip apex. So we can also use the single atom qubits and the sensor to prove other quantum materials, such as the magnetic molecules and other magnetic materials. And also we can use the magnetic atom to build larger spin structures so that we can realize the even exotic states such as quantum spin liquid. And so before I finish, let me also say a little bit about my new lab in China. So this is a picture about the ESRTM at IOP CES, which is the short name for my institution. And we are currently still upgrading the system, and we hope soon we are able to measure this kind of ESR spectrum. So if you are interested, please contact me and we can discuss the possible future directions. And with that, I thank you for your attention.
Thanks a lot, Kai, for this wonderful talk and for telling us about this extremely inspiring results. So now we have some time for questions, and I can perhaps start with a question in the chat. And the question is, I have a basic question that can maybe wait till the end of the talk. Are there any other substrate candidates for hosting ESR-sensitive atoms? Why MgO specifically, in addition to its insulating decoupling properties?
Okay, this is a good question. So at the moment, the only the ESR sensitive substrate we have realized is MgO. So we choose MgO because the MgO is a typical tunneling barrier used in spin electronic devices, and also because the MgO is very stable. For example, very stable thermally. And it turned out the other benefit of the MgO is that it has very little nuclear spins, because here our magnetic atoms are absorbed on top of the oxygen or in between oxygen side. And we know that for the oxygen atom, about 99% of the oxygen doesn't have a nuclear spin. So this can make our T2 time longer. And so another possible candidate substrate you can try, maybe you can try the sodium chloride. But for the sodium chloride, it is not that nuclear spin free. Maybe can make your T2 time worse a little bit.
All right, great. Thanks a lot. All right, so I don't see any questions in the. Oh, there's one more question. Oh, no, there's no other questions in the chat, and I also don't see anything in the participants. So I can perhaps ask one question on my side. So you showed results with a atom with spin 1/2, spin 1, and spin 3/2. So can you give us, let's say, a short summary of all the different spins that one can measure with ESR, and let's say which ones have not been measured, and you think that they would be a natural next step?
Okay, so the atom we have measured, the first one is iron, which a spin 2 system, and also titanium spin 1/2. Actually, it's the hydrogenated titanium spin 1/2, and also the copper, another spin 1/2 system. And so maybe another thing you can try, you just try. This is all the no. We have also tried the cobalt, but and also nickel, and we cannot see the ESR signals. Maybe we didn't try too much, but you can try further. And there's the, I mean, as long as you have the delta M equals 1 transitions for the to ground state, of course you can drive the ESR. There's, yeah.
Yep. All right. Great. Thanks a lot. Oh, there one comment in the chat from Andrea that there's also an iron talosenine molecule.
Oh yes, yes, yes.
Yes.
This is the new result. Yeah.
Yes. Great. All right. So I don't see any questions in the chat, and well, maybe Thomas, do you have a question?
Kai,
Hello, Thomas.
Thank you very much for this fantastic overview and progress report. I have also a technical question on. Sorry, I can switch on the camera. I have a technical question on how big do you think can you make the tip field maximum?
Oh, so that's a good question. So the value we obtain is 10. As you move further, you will reach the point contact. So by that time, there's a abrupt change of maybe the tip apex, or the surface atom may jump to the tip. So that's the limit. Yeah, for the increasement of the tip field. Yeah.
Thank you.
Maybe Jose.
Yes, Sander, please go ahead.
Yeah, Kai, thank you for a very nice talk. And since there are no other questions, let me ask a bit of this question. So in your Outlook slide, you showed this very promising idea of driving multiple spins by basically amplifying one that is not underneath your tip directly. We've discussed this a little bit in the past, but I was wondering, is there any new progress here? Do you happen to have some hidden slides that you would like to show, or I was intrigued.
Oh, there's some new result in Andrea's lab in QNS. So I saw there is a new archive paper posted. So they managed to drive like two coupled titanium atoms using a nearby iron atom. So they can demonstrate like the double resonance by just parking the tip on top of that one atom, and then they can show that they can drive the ESR of both of the atom without moving the tip. Yeah, you can check the archive. Yeah.
I will have a look. Thank you.
Yeah.
Yeah, there's one more question by William. William, please go ahead.
Hi, so I wanted to ask you, in the matrix limitation scripture, why did you use the tip field as the tuning parameter instead of external magnetic field?
Sorry, can you repeat the question? Why do I use the tip field?
Yes, as a tuning parameter instead of external magnetic field. Oh
yeah, so actually we can use both, right? So the external field will change the Zeeman energy of all the spin, and the tip field only change the Zeeman energy of the spin and the tip. So you just have more tunabilities. So the tip field, it breaks the magnetic symmetries between the different spin, and it can detune the system from the singlet triplet state into the Zeeman product state. Yeah, so we can use both. Yeah. But the tip field is more convenient. We just move the tip up and down. We don't have to ramp the external field.
Yeah, great. So it seems that there are no further questions. So, well, there's one more. So Yujong, please go ahead.
It's actually not Yuzhong, but I'm just using Yuzhong's phone. So Kai, nice talk. I have a question. So actually, when you do the quantum simulation, it seems to me that we can only measure one atom at a time. But in, like, for example, cold atoms and other techniques, people can take a snapshot of all the atoms at the same time. So do you think there's a way to go towards that direction and make it more like a quantum simulation?
Well, that's a good question. So for the I think even here, as I shown in a coupled two spin system, a coupled four spin system. So even the tip is only let's say parked only one of the atom, we can still look at the many-body states because all the spins are coupled with each other. So I think the situation you want to realize is actually more close related to the digital quantum simulations, which requires the individual quantum gate operations of different spins. So that is the that is very difficult for the STM setup. So one way to address this, of course, you just put a okay, this is how to drive it. But if you want to detect individual spin, I guess maybe you need to have a coupled spin system with maybe super long T2 time, and then you can move the tape from maybe from here to here, and if you move it fast enough, you can still probe the states of other atoms.
Thank you.
All right, great. So it seems that we don't have any further questions. So I would suggest that we can stop the official part. So Kai, thank you so much for this wonderful talk. It has been really great to see these really inspiring results. And let me say that this is kind of a dream for quantum magnetism, being able to probe this with so much precision and being able to generate these new quantum entangled magnets. And thank you everybody for coming.